Okay, second page of multiple choice. Okay, a 57.8 kilogram sprinter, so that's a mass, accelerates from the starting blocks in a 100-meter race, that's a distance. Okay, if she pushed back with 349 newtons, that's a force. Actually, it says it's a force. What's the acceleration? So we want to know the acceleration. So we've got four things. We want to know the acceleration. We need to know an equation that's going to link all those things together, or maybe just some of them, to find an acceleration. So we're looking for a combination in an equation that has got either mass and force and distance with acceleration. So let's have a look. So we've got speed is distance that hasn't got force or acceleration. So we've got distance but nothing else. Acceleration, yes. Change in velocity, we haven't got that. We haven't got time either. Okay, force we've got, mass we've got, acceleration we want. So that looks to be the one that we want, actually. Anything else that's got acceleration in it? There isn't anything else that's got acceleration. So it's going to be this one. So we've got two things, and we want to find the third one. So we write down our equation. Force equals mass times acceleration. And if we're trying to find the acceleration, we have to rearrange that to get A equals dividing both by m, we got F divided by m. And it turns out it doesn't matter how long the race is, it's the force that she pushes away that makes her accelerate. So the force divided by the mass, we just put that into our calculator. Okay, and it's going to be force, it says force, 349 newtons, divided by, well, the mass is 57.8, 57.8. And I can just do that on the calculator. 349 divided by 57.8, whoops, equals, and that's no use to me, so I've pressed the button again, 6.038, blah, 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 some stuff. Okay, 6.038. The nearest one to that, well, it's been rounded, 6.04 meters per second. The others are too small, that one's too big, so this is the one we want. Okay, number 5. The extension of a spring is shown in the graph as you add different weights. Use the graph to calculate the spring constant of the spring. Now, if you remember, spring constant was the gradient of a graph. If you can't remember that, then actually you've got an equation, force exerted by a spring is the spring constant times the extension. So we could write that one down. Okay, so we've got extension, spring constant and force all linked together. Okay, so we have F equals K, which is the spring constant, times the extension. Okay, and what you could do is either pick a value from the graph, or we can do a gradient of the graph. It actually, because it's going through the origin, works out to be the same thing. So let's pick this value here. Okay, and draw my triangle from there. So from this point, and there's my triangle. You can't really see the bottom part because it's along the axis. So this triangle, the change in height, okay, change in y is, well, it goes from 0 up to 16 newtons. Okay, the change in x goes from 0 to 0.15, and it's in meters. So I'm trying to find the spring constant. So rearranging this, I've got F equals K times E, so F over E equals K. Okay, so that equals force divided by extension. It's the force, you can either just pick 16 or just say it's the change in y because it's the same as for the gradient. It's 16 newtons divided by 0.15 meters, and that's newtons and meters. Okay, and that's going to be 16 divided by 0.15 equals, and I have to press the button, 106.6 what was it? 16 divided by 0.15 equals, and 106.6 recurring, we don't care about recurring, let's see what it really is, 106.6666 forever, okay, which is 106.7. 106.66, blah, blah, blah. Well, 106 and a bit The only one that's close is this one. It's not quite right because actually that would round to 107. But because we're reading from a graph, it could be that this was not quite 16. So this is definitely the closest. That's way too small. This is massively too small. It's like nearly 100 times too small. So the one that's the closest is that one. And that's our answer. Number 6. Okay, a train, and it's got a mass because it's in kilograms, accelerates from that speed up to that speed in this amount of time. Okay, so this is either a speed or a velocity. We'll put velocity. Velocity. Okay, I know that velocity has a direction, but the train is going to be going forward, so that's its direction. 45.8 seconds, that's how long it takes to change. What is the final momentum of the train? Well, we need an equation to find momentum. Okay, and let's have a look. Momentum. Do not get confused with moment. Okay, moment is not the same as momentum. It's got an on the end. Momentum is mass times velocity. Okay, so let's try that. Momentum equals mass times velocity. And it says the final momentum, so we need the final velocity. And there's a lot of things in here that you don't really need. You don't need anything about time. You don't need to know what it starts at. You just need to know the velocity that it ended up at and its mass. So we can just take the two numbers, and it is 25,200 kilograms times the final velocity, 28.9 meters per second. There's all sorts of other things you could calculate. You could calculate its kinetic energy. You could calculate the acceleration because you know the change in velocity and you know the time. You could calculate the force because once you've done the acceleration, you could actually find the force that you need to get that acceleration. But it hasn't asked you to find that. It's asked to find the momentum, which is really easy. It's mass times velocity. So it's just 25,200 times 28.9. 5,200 times 28.9 equals, and that is 72. You can't see that on my calculator, can you? 72,828. And that's not exactly the same as any of these answers, but it's very close to this one. Okay, 72,828, 728,000, 728,000, 728,000. That's the closest. It's just been rounded. I've cleared out these to 0 because they don't count. Okay, it's not this one. That's too small, and that's massively too small. So it's this answer. Okay, it's very confusing because there's much too much information. If it just said the mass, this is how fast it gets, what's its momentum, it's exactly the same question, it's just less confusing.